All right. Anybody have any questions, comments, anything before we get started? Okay. Let's talk about some things we can do with functions. So now that we have a good feel for what first order functions are, the idea that we can store a function in a variable, the idea that a function is just a value, it's just an object just like anything else in Scala. Let's see some of the implications of that and some of the things we can do with first order functions. So the lecture question today, we want to write a method that's going to return a function, something we haven't seen yet, and that's the first example we'll see in the slides, is being able to return a function from a method. And we'll talk about why we even want to do this as well. So write this, this average and range method, and note that this is a capital I. This is average and range camel case. It's one of the cases where I would recommend cut and pasting that right into your code. Make sure you don't have any typo errors. Average and range takes a list of doubles as a parameter and returns a function that takes two doubles and returns a double. So there's a lot of different inputs and outputs going on here. There's two different things going on. A method that takes a list, and that method returns a function, and that function takes two doubles and returns a double. The function that's returned takes two doubles. The first double is a min value, the second double is a max value, and you want to find the average of all the values in the original list that's between those two values. We'll exclude the endpoints, though it doesn't. I always feel weird when we're talking about endpoints with doubles. Doubles, we can always have this truncation error. So the idea of the endpoints being inclusive or exclusive, what do we mean by that? Do we mean inclusive within some variance? Well, is that really inclusive or exclusive? So the safest thing to do, don't test the endpoints at all. I won't test the endpoints either in my testing, in my primary testing. So don't test right at the endpoints, because what does it mean for two doubles to be equal when we can have these truncation errors? It's kind of an awkward thing to talk about, because we might have those truncation errors and end up excluding the endpoints when they should be included. It's kind of iffy. Anyway, in between those two values, what's the average of all the doubles in this original list? And of course, without using var, and you're expected to use some of the methods that we'll see today that work on data structures, as well as returning a function. Then a test suite to test this. Again, don't test right at the endpoints because they're doubles. But if you're encouraged to do, if you're really inclined to do that, this should be exclusive of the endpoints. Okay, any questions on this setup, on what the question is asking? All right. So today's going to be a lot of kind of rapid fire examples. The first one's a bit more involved of an example, and that's just a lot of rapid fire examples of things you can do in Scala with first order functions. So let's just enjoy. So let's wrap up sorting. This is probably the last time I'll mention sorting, at least in lecture. So let's see one more sorting example, and one kind of shortfall of the way that we set up sorting with these comparators. This comparator has to take two elements of the type that we're sorting and return a Boolean, and it has to decide the relative order given only those two values. And when we're thinking about functional programming, we want to strive for what's called pure functions, which are functions that are only that are defined by their input-output behavior only. They can't rely on some external state. Can't rely on state variables of an object that they're contained in, like a method can. They're not concerned with any global state. They have to be pure functions, which means on a given input, it will always return the same output. So if we're trying to compare two values, given those two values, no matter what the state of anything else is, we always want to return either always true or always false with that comparator. So if we want a pure function as a comparator, and if we're thinking functional programming all the way, we definitely want our pure functions. How do we write a comparator that can compare those two values according to a third value? So the example I'll show, if we have 2 points, or two physics vectors as they'll be represented, if we have 2 points and we want to sort them, we want to compare them based on their difference, based on their distance to a third reference point. What we would want is a comparator that takes 3 parameters, but that's not how comparators work. Comparators only take 2 parameters. If we want this to be a pure function, we have to rely only on those 2 parameters. So how do we get this third reference point into the mix? This seems like something that we can't do with our current setup. So how do we get around this? And we're going to do that by creating a function at runtime that's going to have that third argument kind of baked into the function that we create. So what we're going to do is write a method that can create the comparator functions. So I have a method that's going to take in that reference point that I want to sort by the distance to, and I'm going to return a function in the format of my comparator. If I want to sort physics vectors, I'm taking 2 physics vectors and returning a Boolean. That's the type of method, that's the type of function I want to return. So I'm going to create that function with the reference point baked into it, and I'm going to do this at runtime. This is going to give us the flexibility of being able to take any reference point and dynamically creating these functions that have what we would normally use state for, but with that state baked into it. So we can create as many of these comparator functions as we want as our needs dictate. So this method only has one expression. It's going to be building that function itself. Takes 2 physics vectors that it needs to compare, computes the distance of each to the reference point, and then it sorts by the less than operator, so we can have the points closest to the reference point first in our sorted order. So if we want to sort based on distance to this reference point, we're going to call distance comparator. We're going to call distance comparator with the reference point. That gives us the comparator in the format that we're looking for that can just take 2 vectors and is a pure function with those 2 inputs. We'll always return the same output. We get that function, but we create it at runtime and then sort our points based on that comparator that we just created. So now, instead of where we would normally have a comparator that relies on some state, the state being the reference point, we can get rid of that state and have a pure function that we're creating, and we're creating that from a pure method. When this method is given a reference point, it's always going to return the same function, and when that function is created, given 2 physics vectors, it's always going to return the same output, that same Boolean value. So we have a pure method, we have a pure function, we're not relying on state at all, but we still get the flexibility that we had when we could use state, when we were using state to our desire. We can still get that same flexibility, but we're doing it by, instead of having variable state, we have a function, a method that can create functions that change based on the input to the method. And this is how we can construct functions that fit whatever protocol we're trying to fit. A comparator has to take 2 elements of the type we're sorting and return a Boolean. For the genetic algorithm, we have to have cost functions that take in one element, one potential solution of the type that we're trying to optimize, and return a double, which is the cost of that potential solution. So as we'll see at the end of today's lecture, one of the examples I gave as part of the Gen Algo assignment is fitting a polynomial to a list of points. You have a list of points and a polynomial, and you want to figure out the cost. How well does this polynomial fit this list of points? But our cost function only takes a polynomial. So how do we get the information of this list of points into that cost function so I can figure out the cost of this polynomial on this specific set of points? And we're going to do the same thing. We do the same thing like we do here. We have some cost function method. It takes the list of points as a parameter, and it returns a function that takes a polynomial and returns a double, that's that cost function. But that function itself has that list of points baked right into the function. So whenever we want to create a cost function given a set of points, or list of points, we call that method, say, give me the cost function for this specific list of points. It'll give you that cost function for that list of points, and then you can use that for your genetic algorithm. So we have these methods that are returning functions And for today's lecture question, you'll do similar. You'll take two doubles and return a double. But you also have to do the testing, and that's possibly the more important one, at least for your homework, especially if you're doing Gen Algo, is you have the code provided. I didn't have you write I've done it the past 2 semesters, but I didn't have you write the cost function methods that return the functions. But you will have to call those methods. So that testing is important because that's where you're going to see how do you call this method and use the function that's returned, and just getting used to that syntax and that way of doing things. So you have to do that for your Gen Algo when you call my methods that return these cost functions. So any questions on returning functions or any of this syntax or anything that's going on here? This is kind of the last piece of the puzzle. This is the rest of the power that we can get. We can sort anything by any value, any way we want, given this, without having to use any state. Okay. We're going to go rapid fire and talk about a good assortment of collection methods, as the Scala documentation calls them. Collection methods that are going to work with our data structures, methods that we can call on our data structures, and have some function be used and applied to every element of that data structure. They're very useful. Let me backtrack that a little bit. They're not super useful. They're handy and they're efficient. They're more of a different way of approaching problems. So one kind of sad part about today's lecture, we won't gain any more power. There's nothing that we'll do today that you couldn't already have done in 115. A lot of them, this stuff could be done with loops. Most of them could be done with the accumulator pattern that we saw in 115, and I'll reference that quite a few times today. But these are different ways of approaching the same problem. And it's, like I was talking about on Friday, it's a more descriptive way of writing our code. Instead of the accumulator pattern where we're explaining how to accumulate a variable, I'm going to declare a variable, that my accumulator variable, set it to some initial value. I'm going to iterate over my data structure. For each element in that data structure, assign the accumulator equal to the accumulator plus something or times something or concatenated with something, and then return that accumulator variable after the end. Instead of all that, we're just going to have that in one line. We're just going to basically say accumulate this, and let Scala take over the rest. So a lot of it's different syntax. There's also some more efficiency advantages to this. If we're just telling Scala, hey, this is what I want to do, instead of this is how you do it, Scala can work out the how, and we can let that compiler work for us and find some optimizations that we probably wouldn't have found. We can use the compiler's optimizations, which is decades, teams of engineers work for decades, optimizing the crap out of everything. If we want to take advantage of their work, we don't want to start reinventing everything as we go through. So with that preface, let's just take a look at a bunch of these things, a bunch of these methods that make our lives a little bit easier, make our code a little cleaner, I'd say, and lets the compiler work for us a bit more. For each, call some function on every element of a data structure. Probably the simplest one that we'll see. I have some data structure, and for each element in that data structure, I want to call print line. And you can already see that our code gets more descriptive. Like, this is what I want to do, not how to do it. If I put this in a loop and call print line in each iteration of that loop, this is going to be a few more lines, and I'm really explaining to the computer, this is how you do what I want you to do. With this, words for each print line, it almost reads like an English sentence. For each of these elements, I want you to print line. I want you to print it on its own line. So, and notice I don't have the parentheses here for print line. I'm giving it the method in this case, the method itself to the for each method, and then for each is going to call that method on each of the words. Now, arguably for each, maybe not even arguably, for each is not very useful if we're using a pure functional programming approach. We only call for each when we have side effects that we're concerned with. So if we're calling a method with side effects like printLine, with the side effect of printing to the screen, great. For each is nice for us, but if we're in a pure functional programming frame of mind where we don't care about side effects, we don't have mutable anything, no state. Here we're worried about the state of the console, and that's what's being modified here. If we don't have any state, then for each isn't too great for us. But if we're not, when we're not in a pure, immutable, functional programming mindset, for each can have its uses. And I'll use it throughout today's lecture just to call it printLine, just to print things to the screen, not something we normally do in a final product though. So for each calls a function for each element of the data structure. Pretty straightforward for that one. Oh, just getting used to the syntax is the big part there. All right, so let's see some more of these. Filter is going to take a function that takes a parameter of the type of the elements of the data structure and return a Boolean. And it's going to return a new data structure containing all of the elements of the original structure, or rather only the elements of the original data structure for which that function returned true. So I'm going to take my data structure and filter it. In this case, I'm going to filter only the words with length greater than 3. Everything with length less than or equal to 3, gone. Filter those out. I'm going to only keep these elements. And I'm going to use this underscore syntax again. So I want to talk about this again. I could expand this. I could say s:string equal greater than that arrow, and then s.length greater than 3. I can write this out the entire way that we first saw first order functions when we declared them like that. I'm going to take advantage of the underscore throughout today's slides, except in one case, and I'll talk about the underscore notation a little bit more when we get to that case. But I'm going to use this underscore notation, which is shorthand when Scala can infer the type of the parameter. In this case, I'm calling filter on a list of strings, so it knows it's expecting a function that takes a string and returns a Boolean. So it can infer the type, and it's only when I'm using the input one time. If I need to use that input variable more than once, I can't use the syntax, and I'll have to use the more expanded way of writing this. But this underscore is in place of the name of the input parameter. So this is in place of whatever element I'm currently looking at. So this would be each element one at a time, and then filter out based on this function. So I'm only providing the body of the function and using underscore in place of the name of the input parameter. Yeah.
Can you use for each for that?
Yes, but the syntax is a little bit different. I don't recall it off the top of my head, but you definitely can use it for a map.
So I can answer that.
Yeah.
It works exactly the same. It's just going to give you it in key value pairs.
Okay.
For each. So you have to do dot underscore 1.
Yeah, I see. So the underscore will be your key value pairs. So you do underscore dot 1 to get the key, underscore dot 2 to get the value, right? 1 and 2. But other than that, it would work the same way. Thank you. All right. Let's keep on through. Math is this is similar to last Monday's lecture question. I mentioned that again on Friday. I mentioned it again here. Map is going to take a function, apply that function to every element of the data structure, take the return values of that function call, collect those into a new data structure, and return that new data structure that was created using all those return values. So if I have this list, just with the doubles 1 through 5, and I want all those numbers squared, I'm going to say numbers, map. I'm just going to say create a new data structure by applying this function to all the elements of this existing data structure. And then the function definition, again using that underscore syntax, I'm just going to take that input, each element, and square it. So to get the squares, and again, you can see how this is becoming more expressive. To get the squares of a list all in a brand new list, take these numbers, map them onto these numbers squared. You can see they start reading a little more like English sentences. It's more just describing. I want to take this data structure and map it. Once you get used to that usage of the word map, I want to map it onto a new data structure by applying this function. Okay, you could do this with the accumulated pattern. I could say var number squared of type list of double equals an empty list. For each number in numbers, append that number squared to the number squared data structure and reassign number squared to itself each time. And then finally return number squared or print that to the line. We could do that, so we're not gaining any more power here. We can do the same things, but this is a separate way. And of course, as you're painfully aware by now, I'm taking away var, so you wouldn't be able to do that accumulated pattern. You wouldn't be able to say var number squared and then accumulate them. So we want to accomplish the same thing, but by calling this this map method and giving it a first order function. So we get practice with those functions. And in fact, if you go into the map method, it actually is doing that. It's creating a var. It's it's building up a data structure. It's doing that thing. But one, it's going to do it in an optimal way. Again, teams of engineers for decades. It's going to do it in an optimal way that we might not have done. For example, if we're appending on this, appending to the end of a linked list is a very expensive operation that's going to be very inefficient if we're doing it. But map, that's going to be optimized. We're just going to say, hey map, this is what we want to do. Here's the function we want to use. Do this for us in the best way that you know how to do. So let's keep going. Map takes two type parameters. So in the previous example, both those type parameters were double. We were mapping doubles onto doubles. But we can, just by the method, just by the function that we provide, we can change the type in this mapping. So we can map from one type to another by giving it a different function. So here, I'm giving it a function where the input has to match the type of the elements of the input list. So this is still going to be string, of course. But I'm going to return a different value. Here, I'm calling length. That's going to return an int. The map method says, yeah, that's fine. You can return whatever type you want. I just know that my other type parameter is int, and now my type parameters are string and int. And then I can collect those into a list of ints and change that type. Whatever function I give it, it's going to take those inputs, apply that function, even if the types are changing. Since map takes two type parameters instead of just one, it's no problem. We can change these to anything we want. So if you want to map, you have some elements, you need to take this raw data and process it somehow into a new data structure with some values that depend on the initial list, and for some reason you can't use var. This is the way to do it. Map, it's going to take those input values, call this function on each one of those inputs, and return a new data structure with that function applied to each of those inputs, even if we're changing type. No matter what we're doing, we could even be taking in strings and returning functions that take ints and return doubles. It doesn't matter what we're doing here. We can change the type here and collect all those values in a new list. We saw yield last time. And now that we know map, we can draw a connection here. Yield is doing almost the same exact thing as map. So yield and map, very similar. We're going to take some data structure, we're going to apply some code to it, and then we're going to collect the results and put those in a new data structure. So this is very similar to map, very similar syntax. But we're going to use this syntax that we saw on Friday. So we set up our loop. We're going to iterate over some data structure. We're going to put the keyword yield before the body of the loop. And then once we have this keyword yield here, whatever the last expression of the body of the loop resolves to, those values for each iteration of the loop are going to be collected in a data structure, and that data structure is going to be what this entire loop resolves to. So all of this code here, this entire definition of the loop, that entire thing resolves to a data structure filled with the elements of the last expression evaluated in the body of the loop for each iteration of the loop. So you can think of the body of the loop as a function call in this case, or a method call, where the method call resolves to the last expression that's evaluated. When I call, we don't have explicit return values, we don't have to anyway, but when we call a method, whatever the last thing that evaluates is, that's the return value. We can think of the yield in a loop as the same way. The body of the loop is somewhat reminds us of a method call. Whatever that would return, if it were a method call, that's the element that goes in the data structure for each iteration of this loop. So for each number, we're going to run this like it's a method call. Whatever it returns, throw that into a data structure, and then return that data structure from the entire loop. So this entire loop resolves to all those elements, which in this case happen to be all these numbers squared. And then yield is going to try to match the type of the data structure that it was given. In not the type of the elements, not the type parameter, the doubles, but list in this case. We're iterating over a list, so yield is going to try to return a list. Whatever this resolves to, it's going to throw all those in a new list and return that data structure type. Yep.
So is the difference between yield and map is that yield will put it into like whatever you try to define it as, so like oh this is a double, and map will be exclusively maps?
So map will do the same thing in this case. It'll still try to match the data structure. There's we could do this same code. We could say numbers.map, and then this code with the underscore, that'll be the same effect as the yield. They're quite interchangeable. There's I'm blanking on it, but there's subtle differences, I believe. I'm blanking on what they are at the moment. It's possible they're identical, to be honest. And yield also, so if this happens to return a double, but yield, we can also change the type, just like map as well. So yield, I thought I had an example there, but yield can also change the type. If I had my strings here, and this was string.length, we could also change the types here. Whatever that type is that the body resolves to, that's going to be the type parameter of the return list. So yield will try to match the type of that data structure. That if we're just iterating over a list, that's not too important. And really, if we're just iterating over a list, it's more convenient to call .map on that anyway. For my money, this is where I use yield instead of map, is when I'm iterating over something that's not an already pre-built data structure with all my data sitting in there. If I'm iterating over some values like this, if I just want the numbers from 1 to 5, this is where I tend to use yield. It's more of a preference thing, whether you're using yield or map, but this is where I would use yield when I'm not necessarily iterating over data that I already have. Even then, you can put parentheses around this 1 to 5, and then .map. That's going to work for you too. So it's more preference whether you're using yield or map. But here, for the numbers 1 to 5, yield that number squared. Here, since yield is going to try to match the data structure type that I'm iterating over, and I'm iterating over a range in this case, it's not going to be able to match that data type. I can't have a range of doubles, and my loop is resolving to doubles. I have this double type parameter. A range of doubles doesn't make sense. It's just not what a range is. So Scala is going to default to some data structure type, which should be a vector, I believe. It's going to put all these into a vector of doubles. But we don't want to want to have to worry about what that default type is, especially if we need a specific type. If you need a list, for example, just somewhat arbitrarily, if the lecture question says return a list, you just need a list in that case. So if you need a list and you don't want to have to worry about what this data structure is actually going to do, sometimes you don't have to worry if this is just going in another loop, you're just iterating over it. Maybe you don't care what data structure it is, as long as you can iterate over it. But here, if we care, we're going to put parentheses around this whole thing. So this for yield is going to resolve to a data structure with all the elements that we want in it. I'm going to put parentheses around that entire thing. So inside the parentheses is just my data structure, which is a vector of doubles, but we don't want to have to remember or care what that type is. We just want to know what type it's supposed to be. We're just going to hit it with the .toList, convert that to a list, and now we're not thinking about, okay, what does Scala default to if it's iterating over a range with yield? Hit it with the toList, and now I know I have a list of doubles. So if you want to use yield toList, it's going to get you where you want to go. Right. Any questions so far? Yes.
Do a lot of languages have things that are similar to these very functions?
Yes. Yeah, these exist in a lot of languages. So yeah, I'm showing the Scala syntax, but these are all over the place. This knowledge will transfer to other languages. Some languages haven't had these, like Java hasn't had these for a long time, but Java being purely OOP, really OOP mindset, even Java's coming around and starting to add these things in. These are just starting to be more standard out there. You're likely to see them.
Yeah.
Even if you don't use them, you get on a team, somebody on that team is going to use these. It's going to be important to be able to read them. And in documentation that you read, you're going to come across these. It's just become the way to write code. We get sick of writing the same loops over and over.
Yeah, it seems kind of good, so
Yeah.
something I would hope that people use anyway.
Yeah. It's definitely being used out there. Out there in that real world, outside of these walls, it's out there. Anyway, let's talk about this next one. So this is where things start getting a little more involved, a little more complicated, and of course more powerful. Reduce. This is when we want to have a list of elements. We're going to give it a function that takes two elements of that type and returns another element of that type, and applies that function to all the elements of the list to be able to reduce that list into a single value. So here, I want to sum the squares of the numbers in this list. I'm going to give it a function that takes two doubles, returns a double, and that function is going to be applied to all my elements to be able to reduce all this into the sum of the squares. Now the setup for this is very particular. It can be easy to mess up. The function that we give it, I should have named these something other than A and B. In the polynomial example, I named them better. But this first parameter, whatever parameter is the first one, is going to be your accumulator variable. So this reduce is one method call, takes a function and can do the entire accumulator pattern from 115 in almost no lines of code, almost no characters, very compact. So the first parameter is going to be your accumulator variable, and when this function is called on each element, that accumulator, that first parameter, is going to contain all of the results accumulated from every element that came before that element in the list. And the second parameter is going to be the current element that you're looking at in this call of reduce. So my accumulator is just going to have all of the values that have already been accumulated, and I want to add to that the square of the current element that I'm looking at. The accumulator variable is going to be initialized to whatever 0 is for the type that you're using. I have doubles here, so my accumulator is initially 0, And then this function is going to be called on the first element of the data structure. So when I call reduce of sum squares, the very first call to my sum squares function is going to have a equals 0 and b equals the first element of my list. I'm going to take 1 squared, add it to 0, get 1, and then reduce moves on to the next element of my list. Reduce is going to take that 1, that's going to be the new accumulator variable value. B is going to be the second element in my list. We're going to get 4 plus 1, 5. We're going to call sum squares on the next element. A is going to be 5, that's everything that's been accumulated. 3 is going to be my B. We're going to have 5 plus 9, 14. When we move to 4, A is going to be 14. 4 is going to be B, and then 16, and then so on until we get our plus 25, and then 55 for the total value of this. This is the one case where I'm showing the I say old-fashioned, but we just saw it last week. But the first way that we saw to define functions in our code, I'm creating a function. I'm spelling out the parameter names of the body separately, assigning it to a variable with the right types and everything. So all that expanded syntax that we first saw of defining defining functions and storing them in a variable. But we can compact this as well. So I can write this same thing using underscore syntax. Even though we have 2 parameters, I can still use the underscore shorthand for this. The important part here is that the underscores, the order that they appear in the code is going to be the order of the parameter list. It's just the shorthand that the Scala developers decided for this syntax. It's pretty arbitrary, but that's what they decided. It makes sense. I mean, but this syntax, thinking about the question of does this exist in other languages? Yeah, this is a Scala-specific thing. This underscore stuff. But reduce is going to exist in just about any major language these days. Probably not C, but any other language that you're going to see in your careers, you're going to have some reduce functionality. And in C you could write it if it's not part of the standard library yet. So the order that they appear. So the first underscore that appears in my code, in the definition of this function, is going to be the first parameter. The second underscore that appears is the second parameter. And since this is the way, so the first one has to be my accumulator, and the second one has to be the value that I'm looking at, the element for my list. So this is very important to get the order right, that it has to be the accumulator. And this is how we see that we can't use the underscore shorthand if we need to access one of the parameter variables twice. If we need to access a parameter twice, well, how do we specify which underscores for which input? If I use this syntax, meaning I want to use the same input twice, how does Scala know that I meant a function that takes one parameter that I'm using twice versus a function that takes 2 parameters? Scala stuck with 2 underscores means you have 2 parameters, 3 underscores means you have 3 parameters. That's what they went with, that's what we go with. But I can use that same shorthand even though I have 2 parameters. And again, the types can be inferred here. So we can use all this shorthand. And of course, you can see how expressive this is getting. Numbers, reduce this by summing the squares of each value. Nice, compact, clean, readable. And the compiler gets to optimize. Fold is very similar to reduce, but there are 2 reasons why I would use fold instead of reduce. One very important one, reduce always initializes the accumulator to 0. Well, what if I want to compute the, I did call this factorial, just because I happen to have 1 through 5. But if I want to multiply all the elements in a list and my accumulator initializes at 0, well, my result's always going to be 0 no matter what my data is. It's not very useful. Fold lets you initialize the accumulator to whatever value you want. So here I want to initialize my accumulator to 1. And then my function is going to take whatever I've accumulated so far and multiply the next element to it. So now I'm going to get all of these values multiplied together. Since I'm initializing to the multiplicative identity, I don't have to worry about that messing up my results. And I can use fold to be able to combine all these values. Fold actually returns a function. So the syntax might look a little strange. It looks like I have an extra parameter here that's kind of hanging out on its own. Fold returns a function with the functionality that we want. Fold takes in the initial value of the accumulator, returns a function that has that reducing behavior that we want, and then we call that returned function with another function as its parameter to be able to get the full behavior, the full reduction that we want. So we start seeing where we're mixing these things and starting to nest these concepts a little bit more. We have a data structure with a method call that we call that method, returns a function, we call that function with the function as its parameter. Quite a lot going on in not too many characters of code to be able to get this functionality that we want. To be able to reduce a data structure down to a single value based on some behavior that we want. Okay. Any questions on any of this? Yes. Yes. Yeah, I just realized that as I was looking at it, like, why did I call that factorial? It doesn't really... let's give it some nondescript name. It happens to be the factorial 5 just because of the way I set up the question. But yeah, it doesn't make sense for that to be called factorial. All right, let's take a look at polynomials quick and see how we can apply these a little bit. So here I'm calling reduce. You're going to see a little, I'll get to talk about that when I get up there actually. You'll see a little bit different syntax in some of these. Here, I just wanted to be very clear about which one's my accumulator and which one's my coefficient. So I use the expanded syntax here just to be a little more descriptive of what's going on here. So to evaluate a polynomial in this format, and this is part of the GenAlgo handout, this is part of the code that I gave you. Question?
I kind of don't understand what you mean by the accumulator. What does that represent in the function?
So it's like the accumulator pattern in 115. We initialize some accumulator variable and then iterate over our data structure and keep adding in results to that accumulator and then return it. We have the same functionality with that accumulator where this is going to store all of the results of this function call on each element. And each time we get to a new element, whatever that accumulator has in it, that's what that first parameter is going to be at that moment of the execution. So with this reduce call, I'm going to give it this function, and I have this set up for my polynomial where these values are going to represent this polynomial, 1.5 times x squared minus 2.2x plus 5. If I set up my reduce like this, the first time that this is called, my accumulator is 0, and I'm going to add 1.5 to it. The next time this is called, my accumulator is 1.5. I'm going to multiply that by x and add 2.2. So now my accumulator is 1.5 times x minus 2.2, or add negative 2.2. And then the next, when I get to my last coefficient, my constant, I'm going to have that 1.5 times x minus 2.2, multiply that by x. So now I have 1.5 times x squared minus 2.2 times x plus 5. And I can evaluate my polynomials in one line. This one arguably may be a little harder to read than it would be normally. But I can get that done in one line, one call of reduce, to be able to evaluate a polynomial. And then when we want to compute this cost function, what we want, this is thinking back to the first thing that we were talking about. We need some cost function that takes a polynomial and returns a double. How much does this polynomial cost me? According to a certain list of points. So given a list of points, give me a function that's going to tell me how well a polynomial fits those points. I'm going to do that by summing up the squared distance of each point to that polynomial in the y direction. So the x value of the point, evaluate that at the polynomial, get the difference, and then square that. Sum all those up, and that's what I'm going to use as the cost of a polynomial. The sum of the squared distances of the points is the cost of my polynomial. So I'm going to use fold left. The left, you can use left and right on each of these. I could actually just use fold here. It would have the same functionality. Oh, it doesn't. Maybe there is a reason I had that there. Let's ignore that. So fold left and fold right. Means, am I starting from the left or right of my data structure? Am I starting at the beginning of the data structure and working my way through it, or am I starting at the end of the data structure and working backwards? If you're symmetric in what you're doing, that's not going to matter. Like reduce, this really matters which way I'm iterating through this, but the default way, which is left, which is why I don't understand why the other one didn't work. Just reduce reduce both, they'll default to the left version, iterating through your data structure forward. But if you want to go backwards, you would use right explicitly. Now that's bugging me why that doesn't do that. And I have to use fold here because I'm taking a double and a point and I'm accumulating these. So I'm iterating over points, but I need to accumulate doubles. So I need to use fold here because I'm changing the type of my input in my accumulator. So I'm going to accumulate the total distance, the total square distance of these points, iterate over each point, evaluate the polynomial, compute the difference, square it, and then add that to my accumulator. And then after I'm all done with that, after this whole fold left is done, just to keep the numbers small, I'm dividing by the length. Not just to keep the numbers small, but to normalize based on the number of points, I want to divide by that. So if I have a lot of points, I don't want to penalize those polynomials too much. So this is going to return this as a function, and now I have a cost function. How much does this polynomial cost for this set of points? How well does it fit these points? And with that, I'll see everyone Wednesday.